The gamma or X-radiation quanta collide with quasi-free electrons inside the crystalline structure. The collision causes the electron to recoil and emerges a photon. The photons are emerged at angle that varies from 0 to 180 degrees. Ejected electrons can move only ahead, which indicates that the electron emission angle may vary only from 0 to 90 degrees. Instruments used during exploring the Compton effects are radiation source. We used cesium source with energy of 660 kV. Two scintillation detectors. The first one is vertical. Inside the first scintillation detector, the Compton effect is observed. The electron is ejected from an atom and scattered photon appears. Also, the energy of the electron is registered inside this detector. Inside the second scintillation detector, we register the energy of the previously scattered photon. This detector can be rotated into any angle from 0 to 140 degrees. The electronic instrument set contains high voltage double power supply. The voltage is applied from it onto both scintillation detectors. Two spectrometric amplifiers. They amplify signals coming from both detectors. Coincidental arrangement that provides registration of only simultaneous results inside both detectors. That allows us to register only the particles related of the Compton effect. And multi-channel impulse amplitude analyzer, which converts the voltage set on the detectors into number values and puts them on a histogram properly. The ionized particle enters inside the scintillation crystal, which is, in our case, sodium iodide. It causes the scintillation, glaring, inside crystal. Light quanta directed on the photocathode cause the ejection of electrons. Then, those electrons are fastened inside the electrical field between cathode and first of the nodes. The energy of the electrons is high enough for each of them to recoil a few more electrons from the second dnode. This process is repeated a few times inside the photomultiplier tube. This indicates the anode floats a measurable macroscopic electric charge. All the instruments are attuned together to induce electric impulses with voltage values proportional to energy of a particle that comes on the crystal surface. We can observe such impulses on the oscilloscope. First, we have to make a reservation on the experiment. After that, it will appear on the list of previously booked exercises. Then we need to click twice on the name of particular experiment, go to Experiment Management bookmark and turn the power on. The next step is to adjust an angle suitable to make an observation on scattered photons. On this example, we fix 90 degrees and click on Start. Then we can observe the detector rotating onto right angle and fixing its position. The experiment is running now. For the chosen angle, the results should be gathered for about 10 minutes. Now we set 120 degrees, then click on Start. The detector is rotating again onto given angle and beginning gathering the results. In scattered gamma quanta and ejected electrons bookmarks, we can observe histograms that are being built. On the x-axis, the energies of registered particles are presented. From the y-axis, we can read the amount of registered particles. After gathering enough results, we can stop the measurements. The sum of scattered photons and ejected electrons' energies gives us the value of energy of the original gamma quanta. We can observe also that as the scattering angle increases, the energy of photons decreases. The photon's peak moves left. And also the energy of recoiled electron increases. The peak moves right. Two-parameter chart. We can also observe our results on the two-parameter chart. On the x-axis, the energy of scattered photons is presented. On the y-axis, we can read the energy of ejected electrons. As the angle changes, our results should demonstrate the tendency to form the straight line.